Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 9th, 2025. Alright, today we're discussing an ICLR conference paper on the benefits of memory for modeling time-dependent PDEs, published a little over 3 months ago. This paper explores how AI models can better solve partial differential equations, or PDEs. These are equations describing changes over space and time by using memory. When we only see partial data, like low-resolution information, models that remember past states can overcome information loss, outperforming common Markovian approaches, which only use the current snapshot. Alright, so to really see this in action, there's a table comparing different model architectures. It lays out the normalized root mean squared error, or NRMSE, a measure of prediction accuracy where lower is better for different partial differential equations. We see their proposed S4FFNO model, which adds memory to a factorized Fourier neural operator, or FFNO. That's a neural network for physical systems. Consistently achieves lower normalized root mean squared error. For instance, at low resolution, this memory-enhanced model shows up to a 6 times error reduction compared to the standard factorized Fourier neural operator without memory. This really underscores the advantage of remembering past information. Okay, so building on that, this figure really paints a clear picture. The top row shows several line graphs. Each graph plots the normalized root mean squared error against resolution for different models, tested on the Kuramoto-Sivashinsky equation. That's a complex type of partial differential equation, at various viscosities. Viscosity here influences how much fine detail or high-frequency content the solution has. Consistently, their S4FFNO model, shown in red, has the lowest error, especially when the resolution is poor. The bottom row visualizes the frequency spectrum, showing all the different wave components over time for these solutions, emphasizing the significant, high-frequency information that memory helps preserve. Alright, and it's not just about preserving high-frequency details from low resolution. This next figure shows how memory helps when the data itself is noisy. We're looking at the Navier-Stokes 2D equations, which describe fluid flow, and again, we see normalized root mean squared error, this time plotted against different noise levels. Noise standard deviation, on the x-axis, just means how much random static is in the data. In both graphs, for different viscosities, the S4FFNO2D model, that's the orange line with memory, consistently stays below the blue line, representing the factorized Fourier neural operator. This shows memory is also great for handling noisy data. So, shifting our focus from noisy data, this next scatter plot really digs into why memory is so crucial with low-resolution observations. On the horizontal axis, we have omega_f. This quantifies the fraction of unobserved high-frequency Fourier modes, those fine details in the partial differential equation solution that are missed at low resolution. The vertical axis shows the improvement, specifically the difference in normalized root mean squared error between the standard factorized Fourier neural operator and the memory-equipped S4FFNO. As omega_f increases, meaning more fine details are lost, the advantage of the S4FFNO model grows significantly. The color scale shows that lower resolutions, the cooler colors, correspond to more lost detail and thus a greater benefit from memory. Now, to give us a more concrete look at these omega_f values, this heat map lays out that very metric. Remember, omega_f quantifies the fraction of high-frequency Fourier modes, essentially the fine details above a certain frequency cutoff that are lost at a given resolution. The rows show different partial differential equation datasets like advection or the Kuramoto-Sivashinsky equation, and the columns represent various resolutions. Darker blues indicate a higher omega_f, meaning more unobserved detail. So, for lower resolutions and complex systems like low viscosity Kuramoto-Sivashinsky, the high omega_f values clearly show why memory is so beneficial in those cases. Okay, so following on from how that heat map showed us when memory should be most useful, this table gives us a direct performance comparison. It's looking at the Kuramoto-Sivashinsky experiment again, with a specific viscosity. We see the S4FFNO model, that's the one with memory, compared against several versions of the factorized Fourier neural operator, or FFNO, which doesn't have memory at different sizes. The key thing here is the normalized root mean squared error, a measure of prediction error where lower is better, and the number of parameters, which tells us model complexity. Notice how S4 FFNO achieves much lower error, especially at resolution 32, even compared to FFNO models that are much larger. Alright, so to understand how this S4 FFNO model achieves such good results, this diagram shows the general memory neural operator, or MemNO framework. We see input data at different time steps, t equals 0, t equals 1, t equals 2, each fed into an encoder. An encoder is a component that processes the raw input into a more useful format for the model. This then goes to a neural operator, which is a special kind of AI model for learning complex physical processes. Crucially, between stages, there's a memory layer, connecting information from past states to the current one, before a decoder, which converts the processed information back into a prediction. This structure is key to its success. So that memory neural operator framework really provides a powerful way to tackle these complex systems. The big takeaway here is that when we're dealing with time-dependent partial differential equations, those mathematical equations describing changes over time, and we only have partial information, like from low-resolution data or noisy readings, explicitly modeling memory is crucial. This is a big step beyond typical Markovian approaches, which only use the current snapshot of information, and it allows models to make much more accurate predictions, especially when important high-frequency details are missing from what's observed. Thanks for tuning in to the AI Research Roundup. I'm Alex, and we'll catch you next time.